Hi, this paper is a joint work between my group and my longtime collaborator, Elon Ramon at the Technion, and our two students, Tom Allen, who's in the audience and just graduated, and Hedda Hillel, who is the main author. And so previously we heard about caging. So all I'll say is that actually we're going to be focusing on squeezing caging, where the fingers are going in to potentially grab the object, versus expanding caging, but the results largely hold. And as you heard from the last speaker, this idea has been around for a while. In fact, Elon, the co-author, actually was the inventor of sort of caging. So the paper today focuses on a particular, what seems to be quite limited class of caging, which is sort of 3 fingers in an equilateral triangle. But we use a different technique called a contact space analysis, which we'll describe after I describe my own personal journey to caging. So about 5 years ago, I was involved in this DARPA ARM project where teams were given the same robot, and every month we actually had different grasping challenges. And so what would happen is the robot would wake up and it would have to look around and find parts that it knew about ahead of time, but it didn't know where they were going to be. So it had to sort of build models and then extract from those models the identity of the parts. And so you'll see next, after it's built up the model, it sort of identified these things, and then go out and sort of grasp. Now, since we knew the models ahead of time, we could actually sort of design these grasps. But because the sensing was so uncertain, as the last speaker mentioned, because this arm was actually surprisingly uncertain, we ended up actually designing cages almost all the time. And so because the sensing is sort of poor, and in addition, there were many things like picking up cases, et cetera, where we don't need actually a firm grasp. More recently, caging entered my life. I was part of one of the DARPA robotics teams, RoboSimian. And so RoboSimian here actually has 4 hands, so it's a caging dream. And so what you'll see as it sort of gets out of this vehicle here, sort of half of those grasps there are actually sort of loose cages, which accommodate sort of the uncertainty. And then as it goes up here, you can think of this next cage as kind of a reverse gravity cage. After it transforms, it'll sort of open that door by basically caging and slamming down the handle. And this is my favorite cage next. We actually had to turn these valves here. And so we were faster than anyone by far. So caging is a secret weapon. Now, so we could design these cages intuitively, but what we'd like to do is to have a rigorous theory of caging. And so there's a small dedicated community that's largely in this room focused on trying to come up with complete caging algorithms. And so we now know actually how to do caging pretty much completely if we have 2 fingers in the plane. And there are some special cases, and ours is still a special case, although I'll generalize it at the end of my talk, dealing with sort of 3 fingers and higher, where we have sort of 1 parameter, as you'll see later, which open them up. And there are other sort of approximating techniques, and of course the Berkeley group has been leading us into new kinds of cages as well. Now, the work we're talking about here was largely started in the thesis work of Tom Allen and is sort of continuing in the thesis work of the first author. And so our approach, instead of the classical robotics approach of using sort of C-space, uses contact space. So here's the idea, if you don't know anything about caging, from the configuration space point of view, we have a sort of three-fingered object here, and we assume all these fingers are attached to a palm, and so the palm can kind of move in 3 degrees of freedom, but we assume that all the fingers can open and close simultaneously with sort of 1 parameter. So it's a 4-degree of freedom configuration space. So now, if all of the fingers are actually touching this object, then what happens, you can think of configuration space, the object is sort of isolated, and so it's immobilized. But actually, as you open the fingers up, then you actually create a little pocket there, and when that pocket gets big enough, then actually the object can either escape freely or escape into another cage. And so the key thing I want to point out is there's this close relationship between immobilizing grasps and puncture grasp. You find the mobilizing grasp, you'll find a puncture grasp. You find the puncture grasp, you design the cage. Now, instead of working in C-space, what we decided to do is to actually, first, a classical thing is to find the length of distance around the boundary of the object you want to grasp. So it gets rid of really the gripper itself. And then you can actually parameterize each of the locations of each of the 3 contacts here in sort of a 3-dimensional cube, which is really a torus. Now, to understand why you can actually do this projection onto this lower dimensional space, let's dumb it down a little bit and sort of look at 2-finger cages. So we're going to introduce a very simple function, just like they used energy in the last talk, but now this function is just going to measure the opening distance between the fingers. So P of S1 is just where is finger 1 located on boundary point S1, and P of S2 is likewise the location of the second finger at distance S2 around the boundary. Now, what you can show is that actually all the immobilizing graphs, which we know are key for caging, are the minima of this function, and actually all the puncture graphs are saddles of this function. So we can actually look for all the things that we need to design a cage in the contact space. So we actually don't have to work in configuration space. And so the advantage of this then is that actually instead of now a 4-dimensional space for a 2-finger gripper, we're actually down to a 2-dimensional space if we can actually make this work. So here's the idea about how you would use context space search in the 2-dimensional case or 2-finger case. So what you do is you basically start at immobilizing graphs and you sort of slide the fingers all around. And what you want to do is see if you can eventually find what we call a pinching grasp. So if you can actually slide the fingers so they come next to each other, that means the object can escape. So you'll always be able to find this. And so what you'd like to know is that there are many paths in context space which get you to this sort of escape region in context space. You'd like to find the one which actually has the minimum sort of opening parameter. And so we'll call then the set of all locations in context space whose opening parameter is less than a parameter D, the sublevel set. That will play a key role in this work. So the idea then more broadly is rather than searching on discrete paths, what we'd like to do is to actually search by level sets. And so you can think of intuitively what you want to do in the context space is start out with an immobilizing grasp and basically start to flood the contact space distance function, and so that you're now searching over all distances. And eventually when you flood far enough, you get to the escape region. And so the minimum flooding that you need is sort of the size of the opening of the fingers, which you can then use to design the cage. All right. Now, that's a very hard thing to implement computationally. So Tom had a really interesting insight, which is the contact space actually has a natural decomposition into very simple rectangles. So if we have 2 fingers, one of the fingers is always on one edge, and the other finger is on another edge. And so where those spaces overlap in contact space forms a nice sort of rectangle. Now, the thing that Tom proved in his thesis is that the interfinger distance function actually is always convex on each of those things. So all the critical points, which are the things we need to find to design the cage, actually sort of occur on the boundary. And that's just because all the sort of critical points always occur when at least one of the fingers is actually located at a vertex, which is either the corner or an edge of these rectangles here. All right, and so now, rather than sort of searching all those paths in parallel, what you can now do is introduce a graph structure. So we now sort of put nodes of the graphs on all the corners, because we know those are all potentially interesting critical points. And then we put some in the interior edges, which may correspond to special equilibrium. And then we can actually get rid of the contact space and just sort of connect up then all of the adjacent nodes in each rectangle, because we know they have a convex relationship to each other. And then connect up the rest of the graph. And so actually finding the opening cage parameter becomes essential simple graph search. So you can use a Dijkstra-like algorithm to start at an immobilizing grasp and then sort of end up down here at the pinch grasps. And sort of this, what you do is you sort of tune the search so it finds the path with the smallest opening parameter. Okay, but there's a problem with this. And the problem with this is that actually, as you can imagine, we're actually projecting this high-dimensional space on a low-dimensional space. And so we're sometimes going to make mistakes unless we're careful. And so what Tom also sort of came up with was the idea that, hey, we can actually identify all the sort of areas where we make mistakes. There's a few small of them. And what we want to do is use an equivalence notion called sublevel equivalence. So the idea is in the real world, we want to actually project in such a way that the distance between fingers is conserved in the projection. And so now then, what you want to then prove is the caging graph sublevel equivalent to the contact space, and is the contact space sublevel equivalent to the original problem? This direction is easy to prove. The other direction is sort of more complicated. In fact, it's not true, but the way you can make it true is you can basically introduce what we call tunnels. So the idea with the water flooding is if you just drill a tunnel under the earth and you start to flood these other sublevel sets at the same time, you then actually preserve the connectivity in the right way. And so you can find these little tunnels. There's a finite number of them. They're really easy to find and really efficient, and so they don't add much to the complexity. All right, so now let's actually go to the topic of this talk, which is three fingers. And so Halal actually had the interesting idea, well, rather than trying to go for three fingers, because man, we've been bashing our brains against that for a long time, why don't we actually step back and actually look at a special case of three fingers. And so what you show now is if you actually have three fingers that always maintain an equilateral triangle, then actually the third finger, as these move along the edges, always moves inside of a parallel pipette. And so then these motions here are actually forbidden because the third finger, if we're an equilateral triangle, will be contacting these regions. So we actually introduce contact space obstacles, which correspond to those graphs which can be not done by three fingers. So the good news is that almost everything that we did before sort of goes through, and that is you now, by introducing these contact obstacles in this two-dimensional contact space, we now can represent both the two-finger and three-finger cages simultaneously. All the critical points are the same, the local minima, and the puncture points are still saddle points. And so you can capture all the topology, actually, of these three-finger graphs in this two-dimensional space. And so what the paper goes through and kind of shows you then, using these ideas, you can build a similar caging graph where actually the nodes are the ones from before, plus certain points on a limited number of points on the C obstacle boundaries. And so we can actually then search this graph in time n4 to the log n to actually find the caging sets. The real actually contributions of the paper, though, are really mentioning or finding that actually the three-finger caging graph is sub-level equivalent to the configuration space, and moreover, we actually define a topological equivalence between the graph and the original free space as well. So I'll do a small demonstration. So I think this is a wafer first. The students printed up, Halal actually printed up, oops. Actually printed up, made an actual special robot just for wafer to demonstrate this. So here's the canonical problem we've been doing all the time. And so here we're now searching over what you can see in the background is we've constructed the caging graph. We searched over it, and the algorithm actually outputs these sort of regions where you can kind of put the fingers. And so actually Halal actually constructed a special equilateral gripper that actually only moves in equilateral space, just to sort of demonstrate that actually the caging actually sort of works. So let me kind of conclude with the contributions of the paper. So we now have kind of the fastest algorithm out there to actually find three-finger cages of planar objects. But really the main contributions of the paper are sort of the topological and geometric insights into how caging relates to sort of contact space. And the next steps, the most interesting part then is what Lisa were able to show is that every three-fingered mobilizing grasp is a triangle, not necessarily equilateral. And so now you can extend this theory to all similar triangles, so you can actually find all one-parameter grasps. And let me sort of conclude and say that the dirty laundry is spelled out in the paper pretty nicely, but the real problem is caging theory is still far from the real world, even despite all these advances. Thank you.
A question from Michael back here. Way in the back.
Great talk and very interesting paper. I guess the first question I had was, like the equilateral triangle assumption seems like the only place it comes up is really in the parallelogram. So if you went to, for example, additional fingers or a different configuration, do you think there's some sort of analogous structure you could use in the analysis, or does it start to break down?
My gut instinct is yes, there is an analogous one, but it starts to get really complicated. So I think going to four fingers is going to be exponentially harder using this approach. So we're trying to find another approach right now. I don't have a lot of promise for you at the moment.
Great, thank you.
One more question while we set up.